evening talk or discussion. Not quite sure what they're called, but they're always great, always interesting. My name is Robert Hubble, and I work with J.D. Armstrong, or Dr. Armstrong, on some outreach programs. And when he asked me to introduce himself, it's humbling, because J.D. it's sort of a silent wonder, as you know him. You know, I asked him to give me a little bio, so what does he do? He tells me that he's got a bachelor's in physics, of course, from Westminster College to Salt Lake, and he has a master's in Michigan State University in nuclear theory, whatever that means. And then he has a PhD in astronomy from University of Hawaii. Okay, and he came to Maui to work for the University of New Mexico, and he's been working for the Institute for Astronomy for about 8 years. But that's not J.D. We all know that, don't we? Okay, J.D., this really should be changed from the title to What Makes the Sun Shine to How Does J.D. Make Students Shine? Yeah. And I didn't really understand or appreciate it until I saw him give a tutorial on juggling. Okay, maybe if we're lucky, we'll see it. But let's talk about what J.D. does for the students on the island. He works primarily with the FALKS and the High Star program, and the FALKS telescope is a telescope that's dedicated for student use throughout the islands. And he does the programming and makes certain that the students take maximum use of their opportunity to use the FALKS telescope. And if you're not quite sure about the FALKS telescope, ask him later, okay? Because this is his time to shine. The other thing he does, and this is really, really the best part, I don't even have to read my notes, the High Star program, he tutors students. And this is not like tutoring Robert Hubble in math. This is like tutoring someone who's going to be the physicist of the future, another J.D., another who knows who. And if what you don't know is, if you look at how well his students do in the science fairs, okay, always his students do well. And in fact, at the last set of science fairs, he took 6 projects to the state level. And that really is a compliment, and it speaks highly to what J.D. is all about. And so it's kind of cool that tonight he's going to talk to us a little bit about heliophysics or the sun. But we all know that it's going to really be about how he makes people shine. So without further ado, J.D., would you please come in and take this away from me?
All right. Okay, let's do a sound check here. Okay. How's that? Can you hear me? Yep. Is it coming through the speakers in the back? Okay, good. All right. Well, thank you, Robert. I appreciate that. So, no, we really will be talking about what makes the sun shine. And is it back on? Okay, just a moment. We're experiencing technical difficulties because I don't know how to run a microphone. And so we're going to be talking about what makes the sun shine. There's a YouTube video out there by They Might Be Giants. I played it for a little while ago, What Makes the Sun Shine by They Might Be Giants, which was actually a remake of from a previous artist. And so if you're interested, go ahead and look at that, though I'm finding there are some errors in that. But anyway, so let's start off talking about the sun. The sun is about 4.6 billion years old. And it'll, according to the models that we've made, it should last for about 10 billion years as what's called a main sequence star. It's right now a main sequence star. And then it'll spend about 10 million, or about a billion years burning helium into carbon. Currently, it's made of about 73% hydrogen, 23% helium, and what astronomers call metals. And these are the metals to an astronomer is everything that's not hydrogen or helium. So don't go back and tell your chemistry teacher that, or do if you want to taunt your chemistry teachers. The radius is about 700,000 kilometers. Or the way I like to think of it is it's about 2 1/3 seconds light travel time. and it's about 2 times 10 to the 30th kilograms. So let's write that out. Do we have enough zeros there? Somebody count for me. Double check. Oh, look at this. People are actually counting. And if I continue talking like this for the rest of the night, I'm going to put the remainder of you to sleep. I'm sure I put someone to sleep already. Okay, so, well, let's try a little bit more interesting approach to this. Everyone agree? Okay. So let's go on a road trip.
Yeah.
All right. And so, this is our road trip scene. And, well, we need to go on a road trip with somebody, right? Okay. So let's go on a road trip with Phil the photon. Okay? And so we've got the blue is the pointing vector, and the red and green, of course, are the electric and magnetic fields, right? So for anyone that was really into physics, there are a couple people that I know the physics, and they're grinning. So okay, that was successful. And so Phil is generated in the sun. Okay, this is a pilfered image from SOHO, and then I put on the layers of the sun. Phil, let's say that Phil was generated very close to the center of the sun in the core. All right? And what we're going to do is we're going to travel with Phil as he escapes the sun. But let's first of all look how Phil was formed. All right? So how a photon is created in the nuclear core. All right? Well, fusion. Probably everyone knew that. So what we have is we have 4 hydrogen atoms, and they're fused together to form 1 helium atom. Now, when we think about nuclear physics, usually everyone thinks, oh yeah, mass is converted into energy, and that's all there is to it. But there are some conservation laws. First of all, we have to conserve electric charge. So in other words, if we take away an electron, we have to do something because an electron has this fundamental property that's called an electric charge. And it's like the electricity going through our wires. These are the particles that move along the wires as the electrons. But these charges have to be conserved. We also see that baryons are conserved, the number of baryons. And baryons are heavy items, heavy things. They're made of quarks. And the center of a hydrogen atom is a proton. That's a type of baryon. We also have to conserve leptons. These are light particles. So an electron is a lepton. It's a light particle. So if we get rid of a light particle, we have to create a light particle. We can't just convert mass directly into energy. Okay? And then, of course, we also have to conserve this energy mass thing. All right? Now, these other things, why do we have to conserve them? Well, I don't know. We observe that they are conserved, and so after seeing that they're conserved for long enough, scientists decide, well, this is a law of a conservation law, and one of the things scientists really like doing is finding conservation laws, finding things that are conserved, because it makes it very easy to predict the future, and that's what science is about. So if I have 5 leptons, then I can already make a prediction that tomorrow I'm going to have 5 leptons. It makes it very easy to make predictions. So we like these conservation laws. We're going to start with these 4 hydrogen atoms, and I'm not going to go through the details of the process. In the sun, it's the proton-proton chain, and the details are in here, so this is where the Far Side cartoon says, and a miracle happens. Okay? But what we do is we fuse these 4 protons together. We end up with 2 neutrinos. Now, neutrinos are very light particles, so they're leptons. In fact, they're extremely light particles. They're about 1% of the mass of an electron. And we create 2 neutrinos of the flavor of electron neutrinos. So don't worry too much about what the flavor of the neutrino is. Just realize there's two neutrinos. We also produce 6 photons, and this little gamma symbol that doesn't turn out very well in this font, those represent photons. So there we go. So we've got our photons. Here's Phil. Here's Phil's sister, Phyllis. Anyone have a good PH name for the other? What? Phoebe, yes. All right. So we could go through and we could name all these photons. And then we've got these neutrinos. Now, the thing about neutrinos is they're kind of like, cockroaches. You can never catch a cockroach, right? They can go right through walls. These neutrinos don't interact with much of anything. And so they're very difficult to observe. And then we also produce energy, and a lot of this energy goes into the kinetic energy of the particles, the nucleus, and the electrons that are involved. Okay, so we basically start with 4 helium atoms. We end up, or 4 hydrogen atoms, thank you. And then we end up with 1 helium atom. And we end up with 26.73 mega electron volts. It's about 7/10 of 1% of the mass. 7/10 of the mass that went in is this equivalent. I'll get back to that in a minute. So let's check and make sure was everything conserved, because physicists really like their conservation laws. First of all, electric charge. We started with 0 electric charge. These blue rings are the electrons, and in the center of the sun, in the core of the sun, it's about 14 million Kelvin. So these atoms are bouncing around off of each other so fast and so hard that the electrons just get bounced off, and so they're kind of a gas mixed in with the proton gas. So it's just free-floating protons, free-floating electrons. But I've put them here to keep track of them. So we've got 1, 2, 3, 4 electrons, and then the proton has a positive charge, has the opposite charge of an electron. And so we've got, minus 1, 2, 3, 4, and then plus 1, 2, 3, 4. What's the total charge? 0. Okay? Baryons. What did I say baryons were? Heavy things. How many baryons do we have? 4 to start with, and I'll make it easy. How many baryons do we have afterwards? 4. Okay? So 2 protons, and then we also have 2 neutrons. These are neutral charge. Okay? So electric charge before, sorry, we didn't count the charge afterwards. Let's count the charge afterwards. So we've got 2 electrons and 2 protons. These neutrons are like protons. They're very similar to protons. They even have a similar mass. They're made of 3 quarks, just like a proton, but they have no charge. So plus 1, plus 2, minus 1, minus 2. What's our net charge afterwards? 0. Okay. Well, this is good. And baryons, 4 before, 4 after. What about leptons? 1, 2, 3, 4, right? And then afterwards, we've got 1, 2, and then these cockroaches. Okay, these neutrinos. 1, 2 neutrinos afterwards. So did we conserve lepton number? Okay. So there we go. And everything is conserved, right? Yeah, not so right. Was mass conserved? No, this is a problem. So until Einstein came along, we didn't know about this. But I think most of the people in the audience already know about this. So if we go ahead and we measure and we weigh all of these particles before and after, including our neutrinos, then the amount of mass we had before is more than the amount of mass we have afterwards. Okay? And if we write the mass of say helium or carbon or anything else, if we take how much mass there is in that atom, we know how much mass was lost and converted into energy. And here's where our mass went, into this energy. And this energy is mostly kinetic. And so, my animation will work. Oh, I've got 2 copies of that slide. So 26.73 mega electron volts was converted, of energy is converted from mass. So we take a little part of this mass and convert it into energy. And it's 7/10 of 1%. Or 7/10 of 1% of the mass. I can remember that. It's actually very easy to remember the fraction of mass that is converted into energy when forming helium from hydrogen. Does anyone want to know the easy way to remember this? 007. This is 0.007 of the mass is converted into energy. So, you know, being a James Bond fan, I can remember, but that's only a very small fraction of the mass that's being converted into energy. So we're cooking down the material, but we can't convert it all. And this is actually the nuclear reaction that converts the most mass, the highest fraction of mass, into energy. So this is the best place to fuel stars. All right. So, and of course, this is, you know, the nuclear bomb inside of the sun. Everyone's heard that the center of the sun is this nuclear furnace, this nuclear bomb. It's a hydrogen bomb, and it's being balanced by the weight of the sun holding it in. Has everyone heard that? Okay. All right, so let's go to a scenic viewpoint and take a look at the solar core. Okay, let's look at this big, exciting explosion. Everyone ready? Okay, so the power of the sun, 3.8 times 10 to the 26 watts. Okay, I don't even know how many Los Angeles cities that will provide. I mean, it's just mind-blowing power, mind-blowingly large amounts of power. We really can't comprehend this kind of number. The mass of the core. Now, the core is defined as, this is where the fusion happens. This is where hydrogen is fused into helium. That's what we draw as our borderline. And so the mass of the core is about 7.96 times 10 to the 29th kilograms. Now, I weigh about somewhere in the neighborhood of 50 kilograms. So again, mind-blowingly huge quantities. Okay, so that's the core of the sun. And that means it's producing energy at a rate of 0.00048 watts of energy per kilogram. Okay, this is how fast it's generating energy. Is that that's a pretty impressive bomb, do you think? You're shaking your head. Do you want to comment? Seems pretty quiet. Let's see how we measure up to a nuclear bomb. 0.27 watts. It's about 500 times the energy generation rate of the core of the sun per mass. So if we took a per kilogram of me and per kilogram of the sun, I'm putting out 500 times approximately the amount of power. So I guess I'm, you know, super nuclear. All right. So our scenic viewpoint is not going to look very much like this atomic bomb, is it? It's probably going to look more like this. Yep, thank you, blink. So not incredible amounts of energy generation when you consider the mass involved. I've heard it compared to compost heaps or a lizard. That's got to be a pretty sluggish lizard, you know. Okay. So it's not this huge, massive explosion, but it is fusion. It is the way that we have a hydrogen bomb. It is the same energy source. Okay? So above the core, we're going to go to the radiative zone. Okay? The radiative zone extends from about 25% of the radius of the sun out to about 70% of the radius of the sun. Okay? That's about 310,000 kilometers. Okay? All right, so the radiative zone, okay, I just went through that. Now, the temperature drops from about 7 million Kelvin at the bottom of the radiative zone to about 2 million Kelvin at the top. Okay?
Sorry,
No.
head of the class kid caught a typing error.
Oh,
There was another one earlier.
okay. Next time I'll have you proofread for me.
Misspelled scenic and you misspelled density.
Good. Yep. Okay, well, we'll go through the slides afterwards. Okay, density drops by a factor of about 100. So, okay, first of all, the temperature drops from 7 million to about 2 million Kelvin. And at the center of the core, it's maybe about 14 million Kelvin. Okay, now which way is the energy going to be flowing? Outward, right? And if we had something hotter on top of something colder, which way would the energy be flowing? Inward, okay. Energy flows from hot to cold. And if you ever doubt that, try to heat up your coffee by putting an ice cube in it, okay? Heat always flows from hot to cold. This is one of the laws of thermodynamics. And some people know what I'm setting them up for later. So density also drops by a factor of about 100. If we imagine stacking some pillows, the pillow at the top is going to be big and fluffy, right? The pillow at the bottom is going to be really squished down and compressed. So the density is the amount of mass per volume. And by the time we get to the top of the convection of the radiative zone, it's dropped by about a factor of 100. All right, so let's take a look. Boy, I keep forgetting to click my slides forward. Okay, so let's go to our scenic viewpoint for the radiative zone. Okay, so the radiative zone, here's Phil, the photon, and the radiative zone is basically just this gas of protons and neutrons, and also helium nuclei and protons and electrons, so hydrogen, and then also helium atoms as well, and their electrons. But these are all floating free. It's still too hot for the electrons to be held on by their nucleus. And so Phil is going to bounce around from one electron to another. He keeps trying to get out of the sun, but he bounces between electron to electron. It takes about 1 million years for a photon to go from the core of the sun out to the top of the radiative zone. Okay? And it's because it doesn't take a straight path. It keeps interacting with the particles, with the mass in the radiative zone. All right? And the core is the same way. The only difference between the radiative zone and the core, what defines that breaking point is when you stop nuclear fusion. All right? Everyone with me? Did I put everyone to sleep? Okay. Everyone's catching the little red signs? Ah, okay. So next we're going to go up to the convective zone. This is the top layer, sort of like the top layer of the sun. Okay? Top but below the surface. And that's the next, 200,000 kilometers. It's about 30% of the radius of the sun. And the convective zone, instead of the energy being transported by light bouncing around from electron to electron, instead we actually have mass moving. Okay, it's like water turning over in a pot. Has everyone seen, as you put a pot of water on the stove, you get these little plumes driven upward from the heat, and then the cold water sinks down to replace it. In the sun, though, they tell me that it's actually driven from the other direction. It's the cold plumes that form at the top. Okay, so at the top of the radiative zone, all the energy is given off. It's radiated away as light, and so the material cools off. And as it cools, it becomes denser and sinks down into the radiative zone until it gets to the base of the radiative zone, or until it gets to the base of the convection zone. Watch me and throw something at me if I do that again, Connor. Okay, as it sinks, as this parcel of cold material sinks down through the radiative, or through the convective zone, it reaches the radiative zone. Okay, and it basically heats up there. And then once it heats up, well, now you've got this cold material coming down, and that floats up and reaches the top. All right? And we're going to see a little bit more of that once we get to the solar surface. And so the next scenic viewpoint really is the solar surface. And this is sort of an exit-only place, right? This is us leaving the sun. Okay? The solar surface is basically where light stops interacting with the material. But this is a movie that we have of the sun. These are real images that were compiled. And what we see, you'll notice there are these dark areas, and then there's these light areas. These dark areas are where the plasma has cooled and is now condensing, and it's sinking down into the sun, forming these very fast plumes. These plumes actually go faster than the speed of sound in the local medium. So they actually form sonic booms within the sun. And then these bright areas are the warm material that is coming up, that is being displaced by the colder downflow.
What's the scale on those granules?
I'd have to look it up.
How big
I'd have to look that up to make sure I didn't get it wrong, but it's bigger than the granules, I believe. Okay, so and so let's play this movie again, and we can watch the convection going on. Yeah, and does everyone see kind of? It does look a little bit like boiling water, or just before it's boiling.
Rice pudding.
Rice pudding. Okay. Yes, if you put some glitter in your water as you're heating it, it makes it much easier to see. Seriously, scientists, there's someone in this audience that is enough of a scientist that I'll bet they'll go home tonight and they'll take a pan and they'll take some water and a bunch of glitter and be doing this. There we go. No, whatever your color, whatever is easiest to see, you know. Just you're looking for contrast from the pan. Okay, blue. Yeah, blue would be good. All right.
Gold, come on.
Okay, gold works. Gold works.
Talking to the sun, you're gold, right?
Yeah. But here's the thing. Now, what color is the sun? Everyone.
White.
Okay. I heard 2 whites and some yellows. How many people say that the sun is yellow? How many people say the sun is white?
Sometimes I stare at the sun.
Okay. Don't stare at the sun. Unless you get something like a welding mask, or if one of the, there are some solar viewers. In fact, I've got one I'll give you if you'll stop staring at the sun with your, okay. Use that. Okay. Yeah. So this is about the color of the sun. So is it yellow or white? Yeah. It's, I mean, even this part here is still quite bright. It's just we set the brightness contrast. But this is about the color of the sun. It is there's a little enhancement in around green, about where green is. But if you look at the sun through a telescope that has a neutral density filter, one that doesn't change the color, it looks white. So, we learned something, hopefully. All right? So, all right. Shall we continue on our road trip? Okay. So the surface temperature is about 5,777 Kelvin. All right. Here's another thing that I find very kind of trippy. It's not a solid surface. If I come up to this desk, I can feel something, you know, a definite change in density there. If I come up to a puddle of water and plunge my finger in, I can feel a definite surface. But at the surface of the sun is not that type of surface. All it means is this is the last place that light was scattered by the matter. This is the last place that a photon ricocheted off of an electron or a hydrogen atom. All right? Okay. And the density changes very gradually through this area. No real spikes in density change. But it's very thin. It's maybe 100, 200 kilometers thick. But compared to the size of the sun, that's a sharper surface than we're getting on this table. So it's a very big surface from our standpoint, but in scale of the sun, it's actually a very sharp surface. And it's not a surface of density, it's just a surface of where we see. This is how far we see into the sun. That's how we define the surface. Does everyone get that? Okay. Did anyone, I never got to go to one of these mystery spots. Do you mind if we stop by one?
Sure.
Okay. Now what is our mystery spot going to be? Everyone? Yes, our sunspot. Okay, I know a lot of you know what a sunspot is, but let's pretend we don't, okay, just for fun. So here's our mystery spot, this sunspot. These have been observed since, you know, something like 300 BC. And Chinese astronomers, in particular, they could use the sandstorms of the Gobi Desert as sort of a filter and look at the sun, and they'd see these spots. And by about 35 BC, I think it was, this actually became part of a regular report to the emperor. And so they'd have one of the scientists up there, you know, observing the sun, and he'd write down, there's a little black spot on the sun today. And later that was translated into English and became the basis for a song. Okay, so here's our sunspot. Now, if we imagine being early astronomers, the earliest solar astronomers, then this might be something we'd see if we watched the sun for a very long time. This is from NASA's SOHO project. And you see these dark spots. You see where they're emerging. Yeah, some of these are quite big. Some of these are bigger than the Earth. Those are definitely bigger than the Earth, that sunspot group. Okay, should we watch that again, or? Yeah, let's watch it one more time. Okay, so notice that the very first spots emerge very far up north and very far down south, generally, not always. Okay, and as we go further and further along, the line at which the sunspots form, they kind of shrink together. All right? This is an important clue as to how to our model that describes our sunspots. All right? So let's go ahead and draw. This is what's called a butterfly diagram. And this was created by Mondar. He was the first person to do this. And what he did is he went through, and on each day, he made a little dot if there was a sunspot. Okay? And so in 1940, and then the dot up and down, this is the latitude on the sun. So above the equator or below the equator of the sun. Okay? So the first sunspots tend to appear at high latitudes or low latitudes, not near the equator. So let's go through this. And there's definitely a pattern here as well. Does everyone see that there's definitely a pattern? And some wings are bigger than others, some are longer than others, but it's fairly regular. The first sunspots tend to appear, high latitudes and low latitudes, not a lot in the equator. And then as time goes on, they kind of drift towards the equator until near the equator is all the only place that we really see them. And notice there are very few that are right on the equator, quite a few less than even nearby latitudes. So that's kind of an interesting piece of how we understand these sunspots. All right. Another way to plot this is if we plot how much of the area of the sun is covered with sunspots. And we can do that in a graph. And you notice that there is a peak here. And the distance between peaks is about 11 years, sometimes more, sometimes less. All right? Yes?
What are the units on the vertical scale?
This is actually probably number of sunspots. Yeah, yeah. And there's some weird scaling that I never quite followed. But it's basically, think of this as how many sunspots. Okay? Good? Yes?
Why are there no spots on the poles or at the equator?
Well, we'll get to that. I'm glad you asked that. So this is where scientists put together a lot of this, and this is what scientists came up with. We found that sunspots were related to magnetic field. And what we think happens, I'm going to restart that. Okay, this is again NASA SOHO project. This is an animation, and there are these magnetic fields passing through the sun. The center of the sun rotates faster than the poles. So the field, I'm going to keep replaying this until I am happy. Okay, so the field gets stretched here, and these field lines, as they're getting closer together, that means a stronger magnetic field. The magnetic field is being formed at the base of the convection zone. That's where the shear that's stretching these magnetic fields out is the strongest. And there are some details about this model that we're not happy with, that we have not resolved. And I know some of the scientists who have worked on very detailed models like this, and there's some predictive capability, but there are some errors. And so we still don't know this entirely. All right, let's watch this one more time. Okay, so the magnetic field gets wound up. When it gets strong enough, it floats up to the top of the convection zone in kind of an omega loop like that and forms a sunspot. And we're always taught that sunspots come in pairs. One is a North Pole sunspot and the other is a South Pole, so there's a loop. Okay? Of course, that's not always the case. Trust me, I've seen very isolated sunspots and not been able to find what they're connected to, but the field lines have to connect somehow. Okay, magnetic field lines, every one of these lines has no end. It always connects around. They're loops. Okay? And so there will be a sunspot here, sunspot here, sunspot here. And then after a while, all these magnetic fields rising up to the surface of the sun, and they get twisted around when they're rising, kind of like a cyclone. And then they drift towards the poles. And they kind of neutralize the magnetic field there until there's not much magnetic field left, and that's when it flips and goes back to their starting point, which was kind of the bar magnet fields. Now, the bar magnet fields are not strong enough to act as sunspots, and I'll get to that in just a minute. All right, so what is a sunspot? Well, the magnetic fields thread through the plasma. Now, plasma is very electrically conductive, right? All those electrons can move any direction they need to freely and independently from their nuclei. So we can, if I put hooked a battery up to the sun, it would be very low resistance. That current would just go through it, no problem. All right? But that also means that magnetic fields can pull around the electrons. And the rule is that when you have a magnetic field and you have a charged particle, and electrons are charged particles, what else were charged particles? Protons. What about the center of a helium atom? There are 2 protons in there and 2 neutrons, so it's going to have a charge. The rule with charged particles, when you have a strong magnetic field, or when you have any magnetic field, is they'll spiral around it. They can slide up and down, but they can't cross it, because as it tries to cross the magnetic field, it gets turned, and it'll end up spiraling around and around. So think of these magnetic fields as threads, and the material in the sun like beads that can slide up and down on those threads. Over here, there are no threads, so it can go any which way, right? All right. Now, how did we get energy to the top of the radiative zone, or to the top of the convection zone? Convection. And what does that convection mean? What do I mean by convection? Movement, right. So let's think about how we get energy to the top of this sunspot. Okay? Well, we can go up along this magnetic field, and then we get to the surface, we give off our energy, and then what do? But we can't cross, so we've got to go back down through all our friends that are below us. Yeah, you can't slide. You've got 2 beads on the thread, one trying to go up and one trying to go down. Does that work? No. You have to form kind of a loop in order to have convection, right? And it's not, this idealized cartoon loop. And I don't know where my arrowhead went on that, but there is one. And so to have convection, you have to be able to move and form a loop. And with the magnetic field sticking way up out of the surface, you can't form that loop with that magnetic field there. So what's going to happen up here? What's going to happen? Well, the temperature's, all the energy is going to be radiated away, and then what happens to the temperature? Drops. It cools off and becomes a sunspot. So this is actually a very cold spot on the surface of the sun. Now, if you went out camping and had a campfire, this is a lot hotter than your campfire. But compared to the surrounding material, it's much, much darker and much, much colder. Okay? And I actually did some things where we were measuring the temperature of sunspots, and they are much, much colder. Okay?
Is it emitting photons?
Yeah, it's emitting photons.
Why don't we see it as light then?
Because of the contrast. So if we were just looking at it like this, if we were just looking at this little area here, then it's bright like a light bulb. But it's compared to over here, where it's much brighter than a light bulb, then this looks dark. And so dark and light, you kind of have to give a reference. This is light over here, this is dark over here. Okay? So there we go. That's how we form our sunspots. And so the question that Jan asked of why don't we get sunspots near the poles of the sun is we don't get these really condensed bundles of magnetic field poking up through the surface. So we can't really inhibit the convection very effectively. All right? And another feature of sunspots, and part of why I drew this, is that this magnetic field wants to spread out. Once it gets out of the surface, it actually spreads out very fast. It wants to spread out. Oh, sorry, it's Cindy. Thank you, Rob. Or sorry, thank you, Steve. Okay, so For those in the virtual audience, I just messed up someone's name, and Rob Rukowski helped me remember. Sorry, Cindy. So the magnetic fields kind of want to spread out, and it was found, what they did is they measured the speed of sound along little paths like this. They see a vibration here, they look over here and wait for that same vibration to show up, is effectively what they're doing. And it's, of course, mathematically much more challenging. And they see this toroidal loop, this toroidal flow, so like a donut, and the inside of the donut's going down, the outside's going up. And that's what holds the magnetic field together, kind of like the rubber band of someone's ponytail. Okay? And then, of course, if we're going to talk about sunspots, we need to also remember umbra, penumbra. I actually had to look that up. Also, you'll see these other dark spots here. These are called pores, and they're basically smaller sized sunspots. Then you'll also see magnetic features that are called plage. Those are bright near the edge of the sun. And in fact, some of these dark spots, if they were near the limb of the sun, might appear bright. All right. So so we understand the solar cycle is the magnetic field is like we expect for a magnet, a bar magnet. And then it gets wound up, and these loops start coming up here, and then it reverses. And then the direction of magnetic field on this cycle is reversed on that to that cycle. So is it an 11-year cycle? It's a 22-year cycle. All right. Okay. And there are some variations in the solar cycle, but what I'm really interested in with this graph is there is also an irradiance cycle. So the amount of energy we receive from the sun changes. You have a sunspot, that's a dark area of the sun. And so we would expect that if part of the sun is darker than normal, we would be receiving less energy, right? Okay, and if we're receiving less energy, then we actually, well, I'll get to that in a minute. So, but we can see that there are variations in the sun based on these sunspots that are crossing. Okay. What's interesting, though, is that actually we get more, on average, more energy from the sun when there are lots of sunspots. And that's an entirely different lecture, and I'm already putting some of you to sleep, so I'm not going to get into that. And we can actually see the sunspot observations in blue. Okay. The irradiance is in black, and notice that traces the annual irradiance is in red. You can see that very closely mimics the sunspots. It's not perfect, especially this cycle. This most recent cycle was kind of strange, and it's still very strange. But we can use this as a tracer. And if we look for a longer period, we have what's called the Mondar minimum. In the 1700s, the Thames River that would freeze over in the middle of winter, and they could ice skate across it. That doesn't happen anymore. And that hadn't been happening before then. So there's a very strong relation between the global climate and these sunspot cycles. And we have seen that. All right. So the little red signs, did anyone catch all of them? So yes, let's go through it. Let's go back and let's catch all the Burma shave signs. And yes, that's exactly. Let's actually cheat. No, you did not. Okay, so could. All right, mass not conserved, converted into energy. I should have done a slide just with the Burma shave slides. Yep. All right, so we're getting a nice review. The sun, could the sun, contribute to global? Okay. Signs say and did everyone get the pun of signs say?
Yeah.
Yes. So could this, and what do you think? Do you think it's convincing that the sun could contribute to the global warming? Yes. Okay. Well, of course. If the sun is changing the amount of energy we receive, then it will change the temperature here on Earth. I think that's quite clear. And what we're seeing, this is from NASA's GIS. Let me go back to this previous slide. Notice that there's sort of a downward trend here. Okay? So there's a downward trend of this solar magnetic field. Yes?
JD, who's been doing the counting of the spots? I mean, all the way back to 1750.
These are probably from the Vatican. Yeah. Galileo. But we have records back to China, 35 BC. But the Vatican did that. Galileo did it as well. He had smoke. He smoked his lenses, and correct me if I'm wrong. He projected it. So he projected an image of the sun on the wall using a lens. The Vatican also had an observatory, which was basically a pinhole camera. And you'd go into this room, and you'd have a hole in this side of the room, and then you'd go over to the other side of the room, and here's an image of the sun. And then it's very easy to look for sunspots. Yes?
Do those sources tend to agree with each other? Galileo and the Church and the ancient Chinese records, as far as those?
Oh, as far as these, yes. So the question was, do the different sources agree with each other? At which point I was going to say, no, they didn't agree with each other on anything. But on as far as sunspot counts, yes, my understanding is that, yes, they agree. I haven't actually looked into it.
I saw some data on that and it agreed within about 20%.
So Stan says that he has seen data on that, and it agreed within about 20%. Okay, who else had a question or comment?
I had a comment on with pinhole. If
Mhm.
you have any shape that can let the light from the sun in,
Mhm.
if you get if you get a certain distance away from a wall, there will be a point where there's only a circular string of light. And there's only a circle of light, and that's actually the sun.
Yeah. So when Aaron is saying, for those of you who are out in the virtual world, if you have any shape on your pinhole, you only see that shape for a certain distance, and then once you get far enough away from that pinhole, it'll look round. And the reason is that's an image of the sun. And actually, last week I was walking down the hallway by the labs here, and I saw this oval of light on the floor. And I thought, well, I wonder where that's coming from. So I traced it back, and there was a square hole between the two doors. And there was the sunlight coming in, and by the time it got to the floor, it was a circle, but because the floor is at an angle, it ended up being an ellipse. And so very much, yeah, and so I could have taken a card and sat down right there in the hallway and looked for sunspots. Yes, exactly. Most people would have looked at it and said, oh, yeah, there's a light there. No, I said, oh, there's a light there. Wait a minute, where is this? And I literally chased it down with my hand, following it up to the door. And that's this sort of warped mind that becomes a scientist. So if you see your kids doing that, I'm sorry, they're not normal. They're going to be something science-like. Okay, so anyway, back to the solar cycle. So these magnetic, this is sort of a trace of how active the sun is magnetically. And we notice that for the last 15, 20 years, this activity has actually been on the decline. From the 1900s, there was this incline. All right. Well, right now, this is from the NASA GIS satellite, or GISS satellite. Basically, this is a measurement of temperature. There's no really good way to measure the temperature globally, but this is a pretty good proxy. So about 1800, obviously before the satellite measuring, there's this trend of coming up. But in the last few years, it has been consistent with no increase in temperature or even a decrease in temperature. While meanwhile, carbon dioxide levels are continuing to rise. And so there's some interesting data points here. Currently, the models are still in agreement, the models that say carbon dioxide is causing all the global warming. Currently, those are still in agreement with these observations. The predictions are in agreement. But in a few years, if this trend continues, then those models probably will have to be revised if the trend continues. And so that's something to watch for. Now, please do not take this as a sign that you should go out and buy the biggest car you can that gets 12 miles to the gallon. Keep going with those, keep striving for those 80 mile per gallon Vespas. All right? So the sun clearly can cause global climate change, and there's indication that that may be part of our observed global warming. All right? And so there's your Burma shave parody, solar physics. All right. So let's actually go to the next scenic viewpoint, and we're going to be up in the solar atmosphere now. And we're getting very close to the end, so if you are falling asleep, don't worry too much. Okay, so here's the solar surface. Above the solar surface is the atmosphere. And basically what's happening is the density is just dropping off exponentially here. In the chromosphere, the temperature reaches a minimum, so we get to a cold spot. Okay, at that point, and in the chromosphere, we have these spectral lines. We have these spectral lines, basically transitions of the atoms have their electrons. It's cold enough for them to hold their electrons. And you have transitions from higher to lower energy states, or the reverse, that will put very specific lines in a rainbow if you project it out as a rainbow in the spectrum. Okay, so think of that as adding some color to it. But we saw that it's really white. All right, nobody thinks that's amusing, huh? Okay, and that tells me you're about ready to kick me off the stage or something. Above the chromosphere, we have the corona. And here, the temperature increases to over 1 million degrees. So what's heating this? We don't know. Actually, this is we're not entirely sure. Somehow, there was a study that I was involved with where we thought it might be acoustic energy. So these sonic booms from the downward flowing plumes are generating sound waves all through the radiative zone. And those will travel up. They could become shocked and might be able to increase the temperature. I know Scott McIntosh in Boulder was saying that he was talking about magnetic reconnections driving that. But it reaches over 1 million degrees. And this is what's called the coronal heating problem. This is the surface of the sun, which is 6,000 degree Kelvin, is heating up the atmosphere of the sun to over 1 million degree Kelvin. So there's your ice cube heating up your coffee. That just doesn't make sense. And so this is something that we're still very interested in. And then the chromosphere, or the corona, since it's so hot, now heat is the motion of, the random motion of molecules or atoms, right? That's what that is. And the hotter, the faster they're moving. Well, at 1,000,000 degrees, some of these molecules are moving so fast that gravity can't hold them. And so it's the upper part of the atmosphere is actually kind of boiling off in this wind. And we call that the solar wind. Okay? And this is a nice image. This is, Rob, do you want to take a bow for this? And, yeah. This is Comet Ison taken this morning, correct? All right. All right. And so what we have is we have a chunk of ice, and it's getting close enough to the sun that it's evaporating and forming this ball of gas around the chunk of ice. And that is actually being blown back by the light and the wind from the sun. Okay? So if we wanted to see the solar wind, what we would do is we'd go out and put some little particles out there and see if they get blown around by it. Yeah, we'd put some glitter out there. Okay? And that's basically what we're seeing. Is the part of the effect here is the solar wind. The other part is the light actually pushing out the tail. All right?
So, JD, the solar wind is not Phil and his photon buddies. It's mass. It's plasma. It's charged particles.
Yes, when we're talking about the solar wind, it is a wind like you would see here on Earth. It's mass, stuff moving around. Okay? But it's very, very low density compared to our atmosphere. Extremely low density. In fact, if our vacuum chamber got to that low a density, I'd be very pleased, but it doesn't. And we've got a good vacuum system here. Okay? And it is, but they are very fast-moving particles streaming out from the sun. Phil also is streaming out from the sun as well. Okay? All right. And so this brings us to another point of coronal mass ejections. Remember how messed up the magnetic fields got? Think of those as rubber bands that were stretching and twisting, and eventually they're going to reconnect and find a better solution than being tied into knots. And when that happens, you can have a big explosion, a big release of energy that drives mass off of the surface of the sun. Okay? So most of what we see, you can kind of see that there's this wind streaming off from the sun. And it varies because sometimes there's magnetic fields that cover this, and sometimes there aren't. That's a comet there, or an asteroid. Yeah. And actually, this satellite was discovering a lot of asteroids because they were looking close to the sun. Yes?
Is the core of the sun also hydrogen and metals? And if so, how is it the magnetic field that keeps it in a distinguished shape?
So the question is the core of the sun also hydrogen and metals? And if so, is it the magnetic field that keeps it in its shape? The core of the sun is hydrogen and helium predominantly. Okay? Metals are like the seasoning in the sun. It's just a little bit. Okay? And what keeps it in its shape is gravity. Okay? Gravity is a fundamental force. And it's every particle pulls on every other particle. Just a little bit. But all the particles together, so you've got a bunch of particles here. This particle over here feels a little pull in this way, a little pull this way, a little pull this way, and all those add up to the same direction and can make a very strong pull. And so there's so much mass there that the pull added up is very strong and holds it against the outward pressure of the plink thermonuclear bomb. Plink. Okay? Does that answer the question
Yes,
fully?
But I'm trying to understand how something like hydrogen, how gravity, I could understand it for the Earth because the Earth's solid, but how gravity could make something like hydrogen be such a a round shape.
Right. So the question is, how can gravity make something liquid like hydrogen be such a round shape? Because that's okay. Let's imagine.
It does the same to the air.
Yeah, it does the same to the air. But let's imagine. Okay, we have a round shape like this. Let's add a mountain. Okay. All right. Should I turn the light on so that can view good view? Okay. So we've got a mountain. Okay. That mountain wants to come down, right? Okay. And that's exactly what will happen. Hydrogen has no strength to hold up that mountain. So it's just going to squash down until it is a round shape. And in fact, the sun is the roundest object, as we learned a few months ago, is the roundest object in the solar system that we've observed. Okay? And it's just, it's a minimization thing. It's, if we went into vector calculus, I could show you this very easily. It was actually in my dissertation. And I can send you those 2 pages that show this. But it's basically just a minimization. It's and the way to think of it really is if you've got a mountain like this, but you have no strength holding up that mountain, what do you expect? You expect it to smash down.
And then one last question. If the there's lots of talk how from time to time the sun changes the magnetic
Magnetic pole.
moves.
Yeah.
How does is there a history as far back as we've been looking at sunspots that had any kind of correlation to that effect on the Earth?
Okay, so the question is that the magnetic field on the Earth also flips. And is there any correlation between the flipping of the magnetic field on the sun and the magnetic field on the Earth? I don't think there's any correlation, but I could be wrong. I mean,
Not correlation, but influence.
influence. I don't think that there's any influence, but I could be wrong. And here's my reasoning. Okay? And in science, we can disagree with each other, but we should share our reasoning and should share our data and help each other understand the data. So the sun is flipping very fast. Okay? I think it's 30,000 years? 26,000 years we expect the Earth to flip. Okay? So this is just flipping back and forth so much that, I wouldn't expect it to really affect it. Stan, do you know of any?
Well, the fields are so weak compared to the solar fields are so weak out here compared to the Earth. That there is an effect, but it hasn't been measured yet.
Okay, so yes, here's Stan's comment, and I like this. Stan Truitt's one of the amateur astronomers here. His comment is the magnetic field from the sun out at the distance of the Earth is so weak that there probably is an effect, but it's so small that since the magnetic fields are so weak, the effect is going to be too small to measure. Okay? Yes, sir.
Solar winds.
Yeah.
How strong are these winds, and how far out from the sun do they extend?
So the question is, these solar winds, how strong are they, and how far out from the sun do they extend? Well, what do you mean by how strong are they? In terms of speed? Very, very fast. In terms of if I put a sail up, well, there's not enough stuff to really billow out a sail unless they have talked about using these solar cells, but they have to be like a mile square sheet of mylar in order to catch enough wind to really accelerate a spacecraft. They have to be very large.
But they have seen the solar wind effect on comets past the orbit of Neptune.
Yes, and they, Stan's commenting, they have seen the solar wind effect on comets past Neptune. And in fact, it goes out farther than that. It goes out beyond Pluto to the heliopause. There is gas between the stars. And as we're orbiting, we're moving through this gas. But we have this bubble that is that's caused by the solar wind pushing outward. Okay? And that bubble is sort of the limit of how far out the solar wind goes, because at that point it hits this gas that's surrounding us and slows down and stops.
So how fast are these winds though?
How fast are the winds? Do you have a number? Does anyone have a number right off? Because I don't have. Yeah, Rob will. Let me Google that for you. Okay. Yeah, in terms of numbers, I'd have to look it up. I know that sometimes, yes.
Right now, the solar wind is at 364.9 kilometers per second.
Okay. So 300 kilometers per second. Very fast. All right. Good. All right. So the other thing I kind of want to look at real quick is these coronal mass ejections. These are basically big dumps of energy. We actually got hit by one of these shortly after the telegraph system was set up in the northern continental United States. And basically it's this big electromagnetic pulse, and you've got this big long wire that acts like a brilliant antenna, and a big radio wave coming in. It created an electric current on the wire that was strong enough to start fires in the substations, in the telegraph substations. We've seen power outages in northern Canada. Oh, and with that, with the fires in the substations for the telegraph, we actually saw auroras. Auroras were seen in Hawaii, as far south as Hawaii. Okay? So, and we've also seen power outages from solar flares, in particular in upstate New York and Canada, there was a fairly major one. Again, you have long wires that act like antennas to catch the radio wave from this. One of the estimates that we have that Dr. Jeff Kuhn, and I think many of you know Jeff, he's actually given me the estimate that in our lifetimes, and so there's a varying scale there, there's a 90% chance that the sun will do something to cause billions of dollars worth of damage. Okay? And talking to him since then, he said, oh, well, that's a very conservative estimate. That's a satellite or two. So we can reach tens or hundreds of billions of dollars of damage very quickly. And also in our lifetime, we have a 50% chance that the sun will do something that will change us as a society. We see the Anasazi and Mogollon from southern Utah, Arizona, and New Mexico. This is a society that disappeared, and it was because of what the sun was doing. So we think it's very important to study the sun, and hopefully you'll understand a little more about solar physics after this talk. So, yes. Right. Yes, they were worried about the sunspots on the astronauts. And what happens is the Earth has a very strong magnetic field. And these charged particles come into the magnetic field. They'll tend to spiral around just like the magnetic fields of the sun. But you can overload the magnetic field and basically peel it back. Or you can also fill the area where the astronauts are with enough radiation from particles wrapping around the magnetic fields and spiraling, going between north and south poles. There's a neat game online. It was magnetic golf. And it actually has this is basically you have your golf ball is electrically charged, and you're trying to hit it into the cup. And the first one is just, straight shot. Oh, well, that was easy. And then they start adding electric fields and magnetic fields, and one of the final holes is actually the Earth, and you can see how the Van Allen belts form. It's rather amusing. If you'll remind me, I'll show you where that is. It's at scigames.com, I think it is. Yes?
If I can go back to the initial radiation that was emitted during the fusion, and that was gamma radiation.
Yeah, those are gamma radiation.
But when it leaves the the surface of the sun, it's basically visual, plus or minus.
Right.
Is the energy lost in all those collisions what supplies the sun to the heat to counteract the gravity? Is that where that
Okay.
heat generation comes from?
Yeah, so the question is that the photon, when he's first generated in this nuclear reaction, that's a gamma photon. It's very, very high energy. By the time the energy gets to the surface of the sun, most of it's down a million years later. It's mostly visible light. And so yes, what's happening is this very high energy photon is bouncing around, and every time it hits an electron, it can either gain energy or lose energy. Most of the time it will lose energy as it's bouncing around inside the core of the sun, until it gets down to visible range and after a million years and escapes. The energy that is deposited in these electrons, now an electron is charged, and when you have an acceleration on a charged particle, it can give off a photon. And so two electrons whizzing past each other very fast will slow each other down and give off some light. And so you're actually increasing the temperature, but the high temperature will also generate more light as well. Okay? And generally gentler light, yes. Okay, any other questions? So that was kind of the end there. All right. So thank you. Why am I worried that you're applauding? Oh yes, thank heaven it's over.